Hi students, Mr. Epperson here, and today we're going to learn about mole ratios. This is an equation of sorts. This is not a chemical equation, though food is sort of chemistry, but it represents how to bake a very probably disgusting cake. There's no sugar in this chemical equation, in this food equation, recipe really, but there's some basic things that you need in order to make a cake. I'm also missing like milk and things, but let's pretend that this is how you make a cake. These are actually the right numbers of eggs and flour and butter. I looked it up, but I just didn't want to fit everything else in there. So let's say this is all you needed to make a cake. I need 3 eggs, 3 cups of flour, 2 sticks of butter, and I get 1 cake, right? That 1 isn't there, but we know that when we write that, if there's no symbol, then it's a 1. Okay, let's say you're having a party and you actually know that you need 2 cakes. So I could use this recipe and figure out how much stuff I need if I want to make 2 cakes. How do I do that? Well, if I want 2 cakes, then I'm going to need twice as much butter, so 2 times 2 is 4, twice as much flour, 2 times 3 is 6, and twice as many eggs, again, 2 times 3 is 6. So if I can figure out how much I want, I can decide, I can then use math to figure out how much stuff I need, how many ingredients I need. So I can discover a little bit about the relationship between product and reactant, really, or ingredients, by these numbers in front. Now, let's think, though, what would happen if instead of making 2 cakes, I actually wanted to make another little cake, like basically a half of a cake. I'd need that much batter, but I'd want like an extra little half batch of batter. 2.5 cakes is really what I'd be making here. So if I wanted 2.5 cakes, well, how much butter do I need? Right? I can't just double the cakes again and double the butter. I have to use some kind of mathematical relationship in order to calculate how much butter am I going to need. So let's go ahead and do that. Okay, so to make 2.5 cakes, I'm going to have to figure out what the relationship is between cake and butter. Now, I can basically write the relationship between cake and butter as unit equalities. So if you remember, a unit equality is saying this unit equals this many of this unit. One of these makes is equal to a certain number of the other thing. And so in this case, I have 1 cake is equal to 2 sticks of butter, or flipped around, 2 sticks of butter per cake, right? Both of these two things are true. Now, I'm going to use one of these as a conversion factor to convert between cake units and butter units. And this is how I'll solve how much butter I need. Which one do I use? Well, if I use this one, I can't cancel out my cake units. Plus, it doesn't really make sense logically. We'll come back to that. If I use this one, cakes are on top and they're on the bottom, and I can cancel those things out. So I'm going to use those units, I'm going to use that conversion factor to convert from those units to butter units. So let's go ahead and do the math. 2.5 cakes times 2 sticks of butter makes 5 sticks of butter. Now, in that process, I cancel cakes and I get into butter units. And that's why that works. If I had used this one, I couldn't have canceled the cakes out. And it also doesn't make sense logically because cakes, if I have 2.5 cakes and I want to see how much butter I need, if I had 1 cake, I'd need 2 sticks of butter. But since I have 2.5 cakes, I multiply by however many cakes I am trying to make the number of original butter requirement. And I just multiply that times that, and I'm going to get my answer. In this case, I'm dividing by how much butter I need per cake. And that doesn't really make sense at all logically. So I'm not going to use that unit, right? So that's pretty simple. I can calculate how much of a reactant I need, in this case, an ingredient, in order to fulfill how much product I want to make. Let's try it, though, in another situation. So how many cakes can be made with 7 eggs? So if I have 7 eggs in the fridge, right, and I went in there and I opened up the fridge and I said, I'm going to make some cake. I don't have time to run to the store, but I know I have plenty of flour. I have plenty of butter. Like I just went to Costco, I got a big bag of flour and one of those big boxes of all those sticks of butter. I have plenty of those things. But I open the fridge and I'm down to only 7 eggs. How much cake can I make? Or how many batches of cake, really, can I make? we can just say that when we say one cake, we say one batch of cake batter, because that's really what I'm making. So how many batches of cake can I make with 7 eggs? So to do this, it's the same process that I had before. I'm going to start off with my 7 eggs, and then I just have to choose, well, which of my conversion factors am I going to use? Is it going to be, the butter units, the egg units, the flour units? Which one am I going to use? Because in fact, there are relationships from every single ingredient to the cake itself, and from each ingredient to each other. So what is the conversion factor I need to use? I need the one that has both eggs and cake. That's all I need. I don't need to worry about butter. I don't need to worry about flour. I need to think about the one with eggs and cake. But which one am I going to use? The one with eggs on the top and cake on the bottom, or the one with cake on the top or eggs on the bottom? So to figure that out, again, I bring it up and I say, okay, eggs here. Okay, they're not going to cancel. I can't use that one. So if I bring this one over, the relationship between cake and eggs, again, is one cake needs 3 eggs, and there's my relationship. So eggs and cake, eggs are going to cancel, and I end up with cake. So let's go ahead and do the math. So 7 eggs and the eggs are going to cancel, times 1 cake is going to be 7 divided by 3, which is 2.33 cakes. And so 2 1/3 batches of cakes can be made with my 7 eggs. So that could be useful information, right? If you're limited in your amount of an ingredient like that, how much cake can you actually make? Well, you can use the ratio to figure that out. Again, assuming that you had enough of the flour and the butter. If you ran out of those things, well, then you're done, right? You can't make any more. Okay, but this is chemistry, right? We're using much more complicated things than that. Well, not so much, because actually we're using pretty much the same style of arranging these different chemicals into an equation like that. So this is an equation we've seen before. Nitrogen combines with hydrogen to make ammonia. So there's the names down there at the bottom. You can see that if I combine nitrogen, I need 1 nitrogen molecule to combine with 3 of the hydrogen molecules, and I'm going to make 2 ammonia molecules. This is a balanced equation, okay? It's a recipe, it's balanced, and the reason it's balanced is because if I actually count the number of green spheres here, which represent the nitrogen element, it's the same on the left of the arrow as it is on the right. And if I count the number of tan spheres, it's the same on the left. There's 6 here as there are on the right. So it is balanced because there's the same amount of stuff that I start with as I end with. What's also interesting and super, super important about coefficients, now it's 1, 3, and 2, right? 1, 1, 2, 3, and 1, 2. So 1, 3, and 2. Coefficients can stand for one of 2 things, or almost 3 things if you want to think about it. It can stand for a molecule, a single molecule, or 3 molecules, however many the number is in front. Of course, there's technically a 1 here. We can just write the 1 there if we want, or we can just know that it's there because it's blank. But 1 molecule combines with 3 molecules of hydrogen to make 2 molecules of ammonia. I can think about it that way. But because molecules are just a way of counting, I can actually count by moles instead of counting by molecules. And that's actually useful because moles are really the kind of thing that you can hold usually in your hand, right? A molecule is so small, an atom is so small, I'm not going to be able to deal with it in the lab very easily. So I'm going to be, when I'm doing reactions, I'm usually dealing with moles of things, and that's the number we use. And think about it, right? If you're talking about the relationship between eggs in a dozen and molecules in moles, that was a relationship that we talked about, that a molecule is like an egg and a mole is like a dozen. A mole is a way to group things into a bigger number. I can count by single eggs. I can say there's 1, 2, 3, 4, 5 eggs in an area, or I could count by dozens and saying there's 1 dozen, right? One little package, 1 dozen, and there's another dozen, there's another dozen. I can count how many dozens there are if I counted up all those egg cartons. And I can also count by moles, just like I can count by single molecules, I can count by moles. So that's why I'm allowed to go from the number at the front to be representing either a molecule or just 1 mole. So 1 mole plus 3 moles of hydrogen gives me 2 moles of nitrogen. And this is why we learn to balance, because this gives us so much more information. Now that we've had our equation balanced, we can actually do some really good information with it, because I know the molar mass of a molecule, an atom, a formula unit. I know that molar mass for sure. Like, I know it totally accurately because the periodic table gives me that information, and it's been measured and confirmed. So if I wanted to then just go from moles to mass, I could say that based on this equation, if I had 1 mole and 3 moles and 2 moles of all these things, I would have, let's start off with the first one, 28 grams of nitrogen, combining with 6.06 grams of hydrogen. That's 3 moles of hydrogen times 2.02, which is the molar mass of hydrogen gas, H2, makes 34.08 grams of ammonia. So this is the balanced equation actually put in grams number, in a number that is based in grams, that came from the molar mass. So just check this out. If I go over here and look at the ammonia is NH3, and its molar mass is 17.04. Because I have 2 of them, right, I can multiply 2 times 17.04 and get 34.08. But I can also take the reactants and say 1 mole and 3 moles, these different measured values go 28.02 grams plus 6.06 grams, and I'll get the same value. So this is truly balanced, not just in numbers of things, but it's also balanced based on this periodic table values. Those numbers that come from the molar masses, those numbers work out to totally balancing from the left side to the right side of the equation. Pretty cool. So something that we've learned is that coefficients, represented here as the 1, the 3, and the 2, can represent particles, or they can represent moles. So they can be an atom, a molecule, formula unit, whatever the type of chemical is in question here. It can represent one of those, or it can represent a mole of those, or 3 moles, or 2 moles, whatever the number is in front. So that's an important bit of information. So let's apply this with a question. How many moles of hydrogen gas, H2, are needed in order to produce 7 moles of NH3, of ammonia? So if I wanted to produce 7 moles of ammonia, according to this equation, how many moles of hydrogen do I need? Basically, what's the relationship between the amount of ammonia produced and the amount of hydrogen required? And if I need more than 2 moles, if I need 7, or 7.5, or 12.5, I mean, any version of this question can be asked, and you just need to use this conversion factor based on the relationship between these 2 units. So let's think about, how do we solve this question? Well, first, let's start with what we know. Okay, 7 moles of ammonia. That's what I know. And I'm trying to get to moles of hydrogen. So my goal is to get to the units moles of hydrogen. I can convert from moles of ammonia to moles of hydrogen, just like I converted from batches of cake to butter, right? So I've got a lot of different options. If I look at all the different options I have for basically the relationships between these numbers, I have a lot of options, which is going to help me out here. So 1 mole of nitrogen is equal to 3 moles of hydrogen in this equation. I need 1 for every 3. Well, that doesn't help me. It has hydrogen, but it doesn't have ammonia in it. So which one am I going to use? Not that one. This one's 3 moles of hydrogen to 2 moles of ammonia. That one has both hydrogen and ammonia in it. So I want to grab that one. This one is the 1 mole of nitrogen to the moles of ammonia. It has ammonia, but it doesn't have hydrogen. So I don't want these. I want this one. So let's go ahead and we'll take that and bring it over. Next question is, how do I want to get this set up? Do I want to use this one, or do I want to use that one? Which version of this relationship do I want to use? 3 moles of hydrogen over 2 moles of ammonia, or 2 moles of ammonia over 3 moles of hydrogen? If I put this one here, are my units going to cancel? No, they're not going to cancel, because the relationship here not only doesn't make sense, but the moles of ammonia are on top, and I'll be multiplying those together, not dividing. I need to divide the same units by each other so that they cancel. So I'm going to use this one. And now I have my equation all set up, and I'm ready to calculate it. So 7 moles of ammonia times 3 moles of hydrogen divided by 2 moles of ammonia. My moles of ammonia are going to cancel, and 7 times 3 is 21. Doing this in my head, divide it by 2, of course you do this in a calculator, is 10.5. 10.5 moles of hydrogen. That tells me that if I wanted to make 7 moles of ammonia, based on this equation, if I had enough nitrogen, all I need is to go gather 10.5 moles of hydrogen, and I will be able to make my desired amount exactly. So that's using mole ratios to convert between similar types of units within a chemical equation based on that balanced chemical equation. I hope that was helpful.